So hey guys, welcome to the channel CodeChef. If you want to learn competitive programming and boost your knowledge in data structures and algorithm, this is the right platform for you. Every week there are several videos which will boost your knowledge in competitive programming and various video editorials for CodeChef contests. So if you are new to the channel, then do subscribe the channel and turn on the bell notification. Myself Chirayu Jain, I'm a CodeChef educator, and in this video we are going to discuss about Bellman Ford Code. Okay guys, so before discussing the code for the Bellman Ford algorithm, let's quickly understand how we can detect the negative cycle. Right, so let us say that we have achieved a state in which we have found out our optimized results, right? And we have performed n-1 relaxations, right? So we have seen that we need to perform n-1 relaxation to get the shortest path from the source vertex to other vertices, right? So we have got some XYZ results, right? XYZ results over here, right? And according to Bellman Ford's, after n-1 relaxation, we are not going to get the more optimized results, right? So let us take this example. So this is, you can see, a negative cycle, right? So after doing one, let us take, if we are starting from 1, so after performing one cycle, we get the result as -1, -3, +2, which will be equal to -2, right? And after completing this cycle, if we again go to the cycle, it will decrement, which means that -2 plus -1 -3 +2, right? So which will be again be -4, right? So it will decrement when we are performing the cycle again and again, right? So what will happen is, if I perform more relaxations after n-1 relaxations, after these relaxations, if I perform more relaxations, then the answer will be new. The answer will come again less than the previous one, but that is not correct, right? Because this is a negative cycle and the answer is coming less because of this negative cycle. So how we can detect the negative cycle is that after n-1 relaxations, if we perform one more relaxation, and the answer is coming changed or less than whatever we have got in n-1 relaxation, that means that this is because of the negative cycle that is present inside the graph. So what we will do, we'll perform a quick check. We'll perform simple one relaxation after this n-1 relaxation and check that if there is something changed, right? If the answer is coming more or less, and if yes, then that means it will have a negative cycle, right? So this is how we detect the negative cycle in the Bellman Ford algorithm. We'll see in the coding part, it is very easy to detect. We'll see in the coding part of the Bellman Ford algorithm. Also, the discussion was pending that why do we need to perform the n-1 relaxations, right? So let us understand that part as well. So if we are taking the nodes like this, right, 1 and 2 and 3, right, and let us suppose the edges are something like 2 3 with weight something like w1 and 1 2 with weight w2, and there are some more edges if you want to take, right? So what will happen is, if we consider this first, and let us assume that the source was this, right? So initially, except this one, all the remaining vertices will have the weight as infinite, right? And after reaching the end point, that means this last set of edge, only then this vertex is updated. That means 1 is already 0 and 2 will be updated, right? So after the whole relaxation, the last vertex is updated. Then we need to perform again the whole cycle, and then these two vertices will be updated, right? So at max, how many edges that we have, right? How many things that we have is n-1 in this case, right? Number of vertex is -1. At max, these many relaxations needs to be performed so that all the edges, in the worst case, I am trying to give you an example, right? In the worst case, all the sequential edges, right, keeps on updating the vertices that it has, right? So let us take that if there is one more edge, that is 4. So if we have the set of vertices like this, right, 3 4 2 3 and 1 2, so after the first iteration, this will update. After the second iteration, this will update. After the third iteration, this will update, and that's how all the vertices are updated, right? So how many relaxations do we need to perform? That is n-1. So this is a clear-cut explanation why do we need to perform n-1 relaxation. Now let us proceed with the understanding of the code for the Bellman Ford algorithm. Okay guys, now let us try to understand the code for the Bellman Ford. So I have already written the code. Let us try to understand with the help of each and every statement what I have written right in C++. So initially what I am trying to do is I am trying to input a graph, right? So what do we have here is the nodes and the edges, right? So total number of nodes and edges that we have. I input that and I make a graph with the type node, right? So I've made a struct over here, right? And this is the initial vertex, the ending vertex, and the weight corresponding to that edge, right? So according to this structure, I make a graph of size edges that we have, that input all the starting vertex, ending vertex, and the corresponding weight. Then I enter the source, right? Source is very important because from that only we need to consider all the other edges, right? And I'll mark that. So I've made 0 over here. That is by default we are trying to take, but let's take that distance of source is also 0, right? So whatever source we take, the distance of that source will be equal to 0. Now this distance is the distance array that we are keep tracking inside the algorithm, right? To keep updating the whatever distance that we have achieved for that particular node, right? As of now. So this is like for n-1 relaxations, as I have said in the theoretical part as well. I need to perform the relaxation, right, for n-1 times, right? So this is how the relaxation is for all the edges. I am tracking that if the initial vertex distance that we have, the weight corresponding to that vertex, plus the weight which edge has, right, and the final vertex distance, right? If the initial vertex distance plus the weight is less than the final vertex distance, then I am updating the final vertex distance as this, right? That's how simple it is, right? So this is how we keeps on updating it, and this is a simple thing to detect whether a given graph has a negative cycle or not. So if after n-1 relaxations also, if the graph is further decreased, right? So if you find this condition to be true, then what you will do, you will simply make the flag 1, and if the flag is 1, that means we have a negative cycle, right? That's what a simple case is. Otherwise we'll output all the distances of the nodes and with the corresponding vertex index, right? So this is the simple clear-cut description of the Bellman Ford algorithm. And let us discuss about the time complexity as well. So if you can see here, this is not good as a Dijkstra's time complexity, but yeah, it can detect the negative part, the negative cycle as well, and can perform on the negative weighted edges as well. So the time complexity here is nodes into edges that we have, right? N into E, the time complexity. Not good as Dijkstra, but yeah, that's what the Bellman Ford time complexity is. So if we run this particular code, right, so let us see if we are getting the exact results as we have seen. Yeah, so if you can see, for 0 we have the weight 0, for 1 we have 4, for 2 we have 1, 3 we have -2, 0 and -1. So as we have seen in the example also, that these are the corresponding weights that we are getting in the dry run of the example as well. So this is more or less the code for the Dijkstra for the Bellman Ford algorithm. Hope you liked it. So if you like the video, then please do hit the like button, subscribe to the channel, and if you want to know more updates of the videos coming onto the channel, then do join our Telegram group. The link to the Telegram group is in the description. I'll see you in the next part.